Okay, hello, we're recording. Hi, my name is Sergio Garcia. I am going to be quickly going over a lot of the general things you need to know for chapter 4 in physics, which goes over just how forces work, how they collide together, and Newton's fundamental laws of force and motion. So let's just get started by talking about the main types of force. So force typically can be either like a pulling motion or a pushing motion. In most cases where there's contact, outside of contact, there's forces like gravity that cause something to be pulled down to like the center of, let's say, a planet or something. But that's more in fields and that's covered in later chapters. Just as a general rule of thumb, there are four major types of forces right here. And they are tension, friction, normal force, and weight. So what is tension? Tension is any force caused by like a pulling of a rope or cord. So essentially, if you had like a box and you had a rope tied to it, the force created on the box by you pulling that rope, that is called tension, as well as the force acting on the rope because of the weight of the box is also tension. So next, another force that we have here is friction. Friction is a contact force. A contact force is what happens when you have two surfaces interacting with each other. So on this box, the friction force is going in this direction, but it's caused by the contact of this box and the floor that it's touching. So if, let's say there was a rope pulling it this way, the friction force is pushing this way because of the two surfaces that are scraping against each other right here. So just to read the definition, friction is a contact force that is directly parallel to the surface. So you see how these two surfaces interact going in this horizontal line. The friction force also goes parallel to that. Next is normal force, which is in this pink line right here. You see it? So the normal force is also contact force. How normal force works is normal force is a force exerted on an object by the surface it's resting on. So like in our world, let's say you have this box again, right? We're going to use this box as the example. So you see how a box has like weight and is affected by gravity. That causes the box to, stay on the thing and go downwards, right? Because on our Earth, if you just have something, it'll fall down until it hits a surface. The force that keeps this box from going through this surface and hitting the ground is because of normal force. Essentially, when the weight causes the box to go down, the normal force acting on this surface causes it to not go fully down or like through the object or surface. It stays on top of it instead. So essentially, it's like the counteraction to weight. It's what the force that acts upon an object when it's resting on a surface. And this force is perpendicular to the actual surface. So if the surface is going horizontally, normal force is vertical. And then finally, there's the counterpart to normal force, which is weight. That is the pull of gravity of an object. And this is a long range force. We talked about contact forces. Weight is a long range force. Because the way weight works, we have this equation over on the far right. Weight is essentially equal to your mass times your gravitational acceleration. So what that means is, let's say you had an 100 kilogram box, and sitting around, right? 100 kilogram box. And let's say our gravitational constant is 9.8, right? You would have a 9,800, it would be 980 newtons in terms of weight. So the force of your weight for that box, if it was 100 kilograms, would be 980 newtons. So that would be the weight. And let me get my eraser. So that's generally what weight is. Again, it's the mass of your box or whatever object you have times your gravitational acceleration. So now we can sort of talk about general laws for this chapter. So we can talk about Newton's law. So Newton's first law essentially says that if the sum of all the forces equals 0, that means the object is at equilibrium. Now, what does equilibrium mean? You might be asking. So equilibrium is essentially when all the forces of an object, like acting on an object, equals 0. So the best way I could equate that is, let's say the vertical force of this box. So let's say the vertical force, we're still using this box as the example. So the vertical force, which would be sum of force y, is equal to, we see that we have our upward normal force, plus what other force do we have working on this? The weight. And the weight is going in the negative direction. And that equals to 0. That means that our, I'll put an arrow here. So that's an arrow. Our normal force is equal to the weight. What this means essentially is that since our normal force and our weight are equal to each other, they cancel out, which means that the box is neither going up or down. It's at a constant rate, which that constant rate happens to be 0. This also works if you're moving in a vacuum, and let's say you were to, there's an asteroid or like just a rock, a space rock floating in space. If it's moving in one direction without speeding up or accelerating or decelerating or slowing down, if it's going at the same speed in one direction, it is at a constant rate of equilibrium. There are no forces acting upon it. And that actually moves us into our next law, that being Newton's second law of motion. Well, I mean, less so. Back to the first law of motion. If an object is in motion, it will stay in motion. So again, if it's at a constant velocity, if there's no acceleration, it will stay at that speed no matter what, unless there's something that acts upon it or something that stops it. For Newton's second law of motion, it's relatively simple. Essentially says that the sum of forces is equal to the mass of the object times its acceleration. We saw that to be true with that example that we just had. We saw how the vertical acceleration of, for weight. So let's say we're looking for the downward force of this object. We know that weight is sort of a similar concept, except instead of acceleration, it's gravity. And that's because gravity is its own acceleration. Let me get my vanishing pen. These two, those two equations are essentially the same. It's just that this weight equation is a more specific sense when it's talking about downward force of an object. It'll always have to account for weight, while this works for tension if you have an acceleration. It works for friction or any horizontal force if you have an acceleration. It works for all of those. And then for Newton's third law of motion, it states that each force enacted upon an object will produce a force that is equal magnitude and opposite in direction. The example in the book that was used, I thought was really helpful. So essentially when you're walking, assuming that there's no friction on something, I'm sorry, that there is friction. If you were to, let's say, just put your foot on the floor and then push, a force equal to that will cause you to move. So the force that you put on the ground as you're walking will be the same but opposite direction force that will cause your body to move as you place that force onto the ground. That's essentially like how normal force works. It's like the what causes you to repel the surface that you're touching. So it pushes you away from it. So if you look at this equation, it says that F1 in one direction will be equal to F2 in the other direction, where F2 is essentially negative F1. So what this means is that if you were to push down with your foot, right, there will be an equal and opposite amount of force pushing you away from the floor. And that's generally how Newton's third law works. There are many applications for it. So yeah, that's generally chapter 4. It's more conceptual. I'll go into more detail on the use cases for all of these in my next video. So yeah, Thank you for your time.